All right, hello everyone. So indeed my plan today is to discuss a couple of machine learning methods that could be used to help the life of scientists. And I would like to discuss a couple of domains like cosmology, chemistry with you. If you have questions anytime, please interrupt me and then we can discuss those questions with you. The other thing, I don't know much of your background, so if there's something everyone knows, you can just tell me that skip that ahead and then I can move on faster. So here are my collaborators on the machine learning side who help me develop algorithms for scheduling scientific experiments. Jeff Schneider is a research professor in the Robotics Institute and also affiliated with the machine learning department. And Willy, Sammy, and Biswajit, they are PhD students in the machine learning department. So this is my, this slide is about the goal, my goal, what I would like to do. So the goal is to create collaborative assistant, generally for science and for also for manufacturing and for daily life as well. So this is the general framework how traditional scientists work. They have a problem in their mind, and then they have to design the experiments. They have to think of what data to collect and how to analyze that data. And I would like to help scientists to use machine learning for all of these boxes here. So I would like the scientists to interact with AI and machine learning agents and help. And these agents should help the scientists to make automatic discoveries, to find anomalies in the data set, find interesting events, or find even new scientific laws that we didn't know about. I also want these machine learning algorithms to recommend new experiments to run, and I will focus mostly on this today, and recommend what data to collect and how to analyze the data. And ideally, we would like to reach that point when at some point these algorithms are so useful for scientists that the scientists want to list the name of these algorithms as co-author on their papers. Okay, so we are not there yet, but that's the goal. All right, and here are some applications that I'm working on. So I'm working on cosmology problems and astrophysics problems, material science, high energy physics and particle physics, working on computer vision and neuroscience problems. I'm also interested how to use these algorithms in games, how to use machine learning in agricultural problems, quantum chemistry, and recently we started to use machine learning algorithms for art as well, to create art projects with machine learning algorithms. All right, so in the experiment design task, the goal is that given a collection of results from past scientific experiments, we want these machine learning algorithms to recommend new experiments to run. And some of the experiments are expensive in terms of time or money. Some are high quality, some are cheap and low quality, and ideally the machine learning algorithms should consider all of these. So they should consider the costs, and they should also consider the expected information that they might gain from that experiment. And the applied tools that we are using in these machine learning problems usually are Bayesian optimization, Gaussian processes, multi-fidelity learning, reinforcement learning, bandit algorithms, and active learning. For some of the algorithms I'm going to present, we have code available, and you can check them out from this GitHub link. Okay, so we have a machine learning platform that's called Dragonfly that can be used for recommending scientific experiments. And many of these algorithms will build on Gaussian processes, but I don't know how many of you know Gaussian processes. So may I ask that? Who knows Gaussian processes and who knows it? And who doesn't? So that's the majority. So let's quickly discuss Gaussian processes because I will need to build on them. Is it okay? So you know regression, right? Because I think everyone took 601 or 701 or other machine learning courses. And how regression works, that you have input-output pairs. And from the input, you want to predict output. And these are the regression algorithms you might know. Linear regression. Do you know support vector regression? Do we know? K-nearest neighbor regression, or you can use multi-layer perceptron for regression. One issue with all of these regression methods is that for any given input, they output only a real number or a real vector. And what we want to do, we also want to output a confidence of our prediction. And that's what Gaussian processes can help us with. Okay? All right, so ideally, we would like to have regression methods where these are the input-output pairs, as you can see here. And instead of just outputting one function, ideally, we would like to output functions like this green function with confidence. And you can see these shaded areas as confidence. When close to the training data input-output pairs, we have high confidence. The variance of our prediction is small. But far from the training data, we have higher uncertainty. We are not that confident in the prediction. But these will be very important for us. All right, so with Gaussian processes, you can handle these three different machine learning tasks. You can do prediction, saying that given a training data, at any given location x, you can say that this is my predicted value with this confidence. That's one thing. Other tasks you can do, you can predict the expected function. That is, this would be the for any given location x, that would you would check the confidence interval, and it would be the half of that confidence interval. And the other thing you can do with Gaussian processes is that you can say that here are some possible functions that all look compatible with your training data. That, for example, in our case, all the blue, green, and red lines, they all look reasonable. All right, this is how it works in practice. In this case, we have 3 training points. And with Gaussian processes, we can fit curves like this, where blue would say that, that's the most likely function. And we can also output some confidence, how confident we are in the prediction. And as you can see, far from the training data, we are not very confident. Right? And if we have more training points, then the confidence gets bigger. That is, the confidence intervals get smaller. All right, so if you increase the points, you can see that we are more certain about the predictions. If the data is more noisy, then you can see that the variance is higher in the prediction. So this is what you can do with Gaussian processes. Everyone is OK with this? OK? So let's discuss the algorithm for Gaussian processes very quickly, how it works. For that, we need to know multivariate Gaussian distributions. And this is my question for you. Who has never seen multivariate Gaussian distributions? Some of you. OK. But everyone knows what one-dimensional Gaussian distributions are, right? So one-dimensional Gaussian distributions just look like this. This is their density. This is the Gaussian distributions have 2 parameters, a so-called mean and the variance. And this is their density function. Okay, everyone knows that. So it turns out that we can generalize Gaussian distributions from one dimension to multiple dimensions. So for example, a 2-dimensional Gaussian distribution would look like this. It would still have 2 parameters, a mean and a covariance, but a mean in this case will be a vector. That is, where is the mean of this distribution? Somewhere here. And the covariance just indicates the variance and covariance between the different dimensions. And that's a matrix. And density of a multivariate Gaussian distribution looks like this, where, again, mu is a vector, sigma is a covariance matrix, and that's all we need. Everyone is okay with this? So this is called multivariate Gaussian distribution. We will need two properties of multivariate Gaussian distributions. One is that if you have a multivariate Gaussian distribution, then the marginal distributions are also Gaussian. That's one property. And the other property that we will need, that if you condition some random variables on the other random variables, that conditional distribution will be also Gaussian distribution. Okay? So again, here are just sample points from a two-dimensional Gaussian distribution. As I said, the marginal distributions are also Gaussian, but it means that if you project all of these sample points to one axis, that would have a Gaussian distribution. If you project to this axis, that's the other marginal distribution that has Gaussian distribution as well. The conditional distributions are also Gaussian, which means that if you fix any point, say this point, and just along this axis, you check the distribution of these points, that should be Gaussian distribution. And similarly, if you condition on this point, then you check the distribution along this axis, that has to be Gaussian. Okay, so these are multivariate Gaussian distributions. Okay, the other thing we will need to discuss is how to generalize Gaussian distributions to even higher dimensions. So we discussed what are one-dimensional Gaussian distributions, what are two-dimensional Gaussian distributions. We could similarly create 100-dimensional Gaussian distributions, but we could even generalize this further and create infinite-dimensional Gaussian distributions. Okay, that's the next step that we will need. Generally, I have difficulty with visualizing Gaussian distributions in bigger than 2 dimensions or 3. So for example, if I want to visualize an 8-dimensional Gaussian distribution, I don't know how to do it, to be honest. What we can do is that we can create an index set from 1 to 8. Those are the coordinates of an 8-dimensional vector. And for each coordinate, I can visualize the mean and the variance. So for each of these index, I create a Gaussian distribution, just a one-dimensional Gaussian distribution that has a mean and has a variance. So for example, this guy with index 5, it has a mean and a variance. This way, I created 8 Gaussian distributions. And another thing we can also do, that we can introduce covariance between these 8 Gaussian random variables, and that I could represent with the 8 by 8 covariance matrix. Okay? And now the question is how to generalize this even further. So one generalization could be that instead of just having 8, the index set should be 1 to 8, maybe the index set could be all the integers. Why not? For all integers, I could associate a Gaussian distribution with some mean and variance. And then what I need is just to tell you how these Gaussian distributions, now I have infinite many Gaussian distributions, how they are correlating with each other. And if we did that, then we can even go further, and you can ask why just have index set of the integers, why not have index set of all the real numbers? So to each real number, I could also associate a Gaussian distribution with some mean and variance. And if you think that way, now for each real number, there's an associated Gaussian distribution. And I can also sample from the Gaussian distributions. And when I sample from all of these infinite Gaussian distributions, actually I just sample the function, where for any real number, there would be a sampled value. And if I set up the correlations right, saying that, for example, if the indexes are closer and closer to each other, then the correlation is higher and higher, I can even sample continuous functions this way. All right, so you can imagine that here, all these real numbers are just indexes for a Gaussian distribution, and I can generate samples from those Gaussian distributions, and then I can sample functions this way from Gaussian distributions. And if I have two indexes x and z, what I want to generate continuous functions is that the mean of these Gaussian distributions should converge. So the expected value of f of z should converge to f of x. And if the index x and z are converging to each other, then their correlation should be higher and higher. And this way we can generate continuous functions. For each x index, I told you that there's a Gaussian distribution. The mean of that Gaussian distribution is denoted with mu x. And for any x and z index, their covariance is denoted with this k function kxz. Okay, so that's just a very quick intro to Gaussian processes. Another thing you can do is that we just rendered for each real number a Gaussian distribution, but we could do even further and generalize that, say, in 2 dimension, where for each point in the 2 dimension, you could generate a Gaussian distribution. And this way, we could sample surfaces, random surfaces, not just random one-dimensional functions. So these are Gaussian distributions. Generally, they are parameterized with, when we are talking about Gaussian processes, they are parameterized with a mean function mx, which is at the index x, what would be the associated mean, and the kernel function k, which just described that between index x and x tilde was the covariance between the associated Gaussian distributions. All right. So this is how we can generate random functions with Gaussian processes. And now let's see how we can use that for regression, because that was our main motivation, to use them for regression. And here I'm just describing the pseudocode of Gaussian processes, and then we can discuss why they make sense. So we have input-output pairs. Say we have a training data of d-dimensional points, and we have n d-dimensional points in our training data, denoted with this set x. Okay, so these are our training inputs. We also have some training targets. We want to do regression, so we have input-output pairs. And those training targets are denoted with this y vector, y1, y2, yn. We have n of these points. This is our training data, input-output pairs. We will use Gaussian processes. As we discussed, Gaussian processes have a parameter, k, which is a covariance function, which just describes that between two indices, what should be the covariance between these two Gaussian distributions. So this k matrix, in this case, so this k function is so this is called covariance function, and it maps, it has 2 arguments. Each of them is a d-dimensional vector. This is our training data. This is the parameter of our Gaussian process. And what we want to do, that when we have a test point, in the test point, we want to output what would be the expected y with some uncertainty, right? That's the goal. And this is how we do it. So first, we will assume that yx, your observations, are just some function of x plus some noise. So that's the standard regression problem, where the noise can have some 0 mean and sigma squared Gaussian distribution. And OK, so this is the pseudocode. So first, from the training data, you create an n by n gram matrix. So remember, we had n input points, each d-dimensional input points. You can calculate the kernel value between any of these xi, xj pairs, and you can create this n by n gram matrix. That's one thing. Another thing we do, that we also create an n-dimensional vector that just contains what's the kernel value between the n training points x1, x2, xn, and x star test point. Okay, so we created this n by n matrix and this n-dimensional vector. Using these, plus using this n-dimensional y's, which were just the target values in the training set, we can calculate this alpha n-dimensional vector. And then it turns out that the mean we can predict has this form, and the covariance in F star, our confidence, is given by this expression. So what you should know, you shouldn't see why this algorithm makes sense, but what you should see that you can run this algorithm, and then at any given point X star, you could create a prediction that would be F star and the uncertainty. That's all we need at this point. Okay, so this is how you do regression with Gaussian processes. All right, any question about this? So what you should see at this point again, we have input-output pairs, and we can use this Gaussian process regression to output a prediction with some uncertainty. That's all what we need. And I have some slides why it makes sense, but I would like to skip that. It's not that important for us. I just want you to know that we can use Gaussian processes for regression, where again we can output not just the predicted value, but the uncertainty as well. All right, and here are some results on this function. The circles are our training data, and the Gaussian, this dashed line is the true function, and the Gaussian process regression provides you this black curve as the mean function, and this is my uncertainty of the predictions. You can see when I don't have training data, then my uncertainty is pretty big. Okay, that's all we need. So that's the take-home message from Gaussian processes, that Gaussian processes can be used for nonlinear regression, and they can provide confidence of the estimate. That's all you need to remember. Okay? And now I want to use these Gaussian processes for scientific experiment recommendations. And the framework we will use is called Bayesian optimization. Bayesian optimization, as its name says, it's an optimization method where we want to optimize a function. We want to find a maximum of a function or a minimum of a function. But we will deal with the case when evaluating the function is very expensive. And typically that's what happens in scientific experiments, that the experiments might take a long time or take lots of money. So evaluating these scientific experiments can be very expensive. All right. The other thing is that when we optimize these functions, we will think of them as black box functions where even the gradient is not available. Okay? So we cannot just think of like neural networks that I can calculate the gradient and do gradient descent. All right? This Bayesian optimization that I will discuss with you, it has been used for hyperparameter tuning for several machine learning algorithms, scientific experiment design that we are going to discuss. It was used for online advertising, discovering new scientific laws, and so on. Here is one specific problem that we are working on, and this is a chemistry problem, where the goal is that we want to find the best battery in the world. And how we do it, that we mix different electrolytes, and we test the properties of those electrolytes. And we want to find that mixture that has, say, the largest, some chemical properties, say, largest conductivity. Okay? The question is how to mix the different electrolytes. Each mixture can be thought of as an experiment. And when we are done with the experiment, we measure the properties of this chemical mixture. And based on those results, we need to recommend new experiments. That is, what should be the new electrolytes to try and how much to mix them. Okay? So here you can see a platform that we built. So we have this platform that can mix different electrolytes and run some chemical experiments on this mixture. And then we combine this chemical experimenting system with our machine learning controller that will recommend new experiments to run. That is, it will recommend new electrolytes to try and portions for them to mix together. So just once more. So these are different chemicals that we can mix together with different portions. And after you are done with the mixing, then we check the properties of this mixture. And based on those results, we will recommend new experiments to run. Yep, anytime.
Is this all automatic?
Yeah, it's all automated. So
this took time to build, right?
So it took like 6 months to build this system. And here we measure the conductivity of the mixture. We got the result, and then the machine learning platform will recommend new experiments to run. Yep.
Can you visualize the maximum that you're getting over time? Do you see it going
So I will show some results for that.
And what features did you use for your electrolytes? What are like the input?
So I will come that. So we will discuss that, but I want to mention another scientific problem where this is a so-called wire cutting machine, which has 20 different parameters, and depending on how you set up the parameters, either this machine can cut aluminum very quickly or very slowly, but with higher precision, and sometimes even the operators don't know how to set up these parameters. But what they can do is that they can make experiments with this and then collect the properties of the cut they made. And next time, from these training data, based on what they want, we can recommend them parameter settings for these machines. All right, and finally, another scientific problem I want to mention is a cosmology problem. So for me, it's very exciting that we don't know anything about our universe, or we know very little. So I don't know if you have heard of dark matter or dark energy. So it turns out that dark matter and dark energy is like 95% of the universe. The normal matter is just 5%. So when you look around here, whatever you see, it's only 5%. There's 95% something else. We have no clue what that is. But they are in the form of dark matter and dark energy. And there are cosmological models that can use dark matter and dark energy. And these cosmological models have some parameters. And our goal is that using scientific observations from telescopes to estimate the parameters of our universe. Okay, so there are theoretical cosmological models. These models have some parameters, and no one knows the exact values of those parameters, but we want to know. Like this, yep?
Sorry, finish your
No, go ahead.
I was just going to ask, these three problems that you're showing us, do they share anything in common in terms of...
We will use the same tools for solving.
Tools, yes, but how did you know that you could use those same tools for all three problems? Because they seem like very different.
Right, so scientifically they are very different, but they all share the same thing that at the end there's some objective function that you want to maximize, and evaluating that objective function is very time consuming. So for example here, in the cosmology problem, so this is the model that we are dealing with, that the universe has some true parameters that we don't know. That those two parameters generate the real universe. We cannot observe the whole real universe. We just can make some noisy observations with telescopes, and we got some observations. We can have some hypothetical parameters of the universe as well. And using mathematical models, assuming these parameters, we can create simulated observations. And then we can check how close our simulated observations are to the true observations. And based on that, we can tune these parameters. We want to find the best parameters where the simulated observations are as close to the true observations as possible. But the difficulty is that simulating universes from these parameters, that's very time consuming. So again, we have an objective function that we want to optimize. We want to find the best theta, but this optimization is very time consuming. Yep?
And there's no relationship, there's no properties across all of these objective functions that are similar.
No.
So you could basically any objective function.
Exactly, yeah.
But in this particular problem, there is also this simulator, mathematical model, right?
Right, so there's a simulator, and we assume that the simulator is reasonable. So that's coming from the physicists.
Yes, it can, but it's still very expensive.
It's very expensive to yes.
I see.
Yes.
But it can very well be that there's no such simulator. Do you agree? And that you only can change your parameters, get the real observer from the telescope, and fit that objective function, right? Or no?
So in this model, we assume that there was a simulator who can...
like for the battery project.
In the battery...
You just have features and then conductivity, right? And we try to work them up.
That's correct. Yep. But there, the assumption was the scientific experiments that those are time-consuming.
Yes, exactly.
Right. Yep.
So we can still get rid of the expensive simulators, right?
So not in this cosmology problem.
Oh.
We don't have that simulator in the chemistry problem.
Oh, okay. So it's just like a trainable selection.
Right. Yeah. Yes. So here the assumption is we have a cost function. We want to optimize that cost function, but that's expensive to evaluate the cost function at each theta. We don't even have gradient in theta. And we want to find the best theta somehow.
So what if we would eliminate the simulator
Mm-hmm.
and we just have the first pathway? We would do worse, of course, right?
Right. So if you just have the first, so that's what the universe gives you. That the universe has true parameters.
Yeah.
And you can make some observations. But then when I assume some parameters, I should have a loss function. How to...
I can be fitting on the real parameters. Like, I'm trying to learn a predictive model of the universe, and this predictive model has some parameters.
Right, so we need a predictive model, a parametric predictive model. Right, and that's true that if you want, you can replace that parametric model instead of a simulator with something else. Right? So that could be, if you want, it could be a neural network. But here the assumption was that physicists, they already know something about the universe, so we wanted to use those simulators.
Right. And then we try to fit observations.
Exactly. Yep. All right. And the trick here, that what we are going to do, that for each theta, you can generate... yep, you have a question? So for each specific application, the kernel function has to be different.
So that means some kind of prior knowledge.
Either knowledge or you try many different ones and choose the best. Yeah, but there's no...
When you see the best, that gives you better fitting.
Right, so the error is smaller, say.
Which is totally fine. You can
Yep.
totally run tons of them in parallel.
Right.
This doesn't
Yep.
cost like-
And you can learn the kernels as well. So there are algorithms for that one as well. Yep.
So based on different problems, because you also have different sort of constraints. Like the second problem when you are cutting the wire, are there like budget constraints, which also you need to enter into your model?
Right, so you can either have money-wise constraints. Like for example, sometimes with the chemistry examples, some of the electrolytes might be more expensive than the others. That could be one kind of problems. But the other kind of constraint could be time constraint. And there's a third kind of problem that I didn't mention, that we have algorithms for something called multi-fidelity learning problem, where depending on how long you run an experiment, you can get higher fidelity, higher prediction, but it's more expensive as well, and you want to consider that one as well. So for example, with neural network, if I want to find the best neural network, depending on how much training data I use, the more training data I use, the closer I get to the true accuracy, but it's more time consuming. All right, so back to this. So what we are going to do, at least in this cosmology problem, that for each theta, I can run a simulator, and then I can check how good this theta is. And I can do that for a few, say, hundreds of thetas. And then I will have thetas and, as input and loss as output. And then I can fit a Gaussian process on these with regression because I have input-output pairs. And now I can minimize my Gaussian process because the Gaussian process, that's just a function that my machine learning model gives to you. I can very quickly evaluate that Gaussian process, but I cannot quickly evaluate the real world. Okay? So what we do is that we try to approximate this map with a function and minimize that function. That's the main idea. Okay, so for example, this is how it works in an abstract level. Here is a function that I want to optimize. In this case, I want to maximize this function. And there's one such algorithm that can do that. That's called Thompson sampling. And what you do is that you start in a random point, say in this point. And for this point, with the Gaussian process, you fit a curve. So that might look like this. And then you find the maximum of this point. And you can do that quite quickly because, again, it's a Gaussian process that you generated. You find the maximum of that, and then you make a new evaluation. You find the maximum of this new curve. Then in the maximum point, you make a new observation. You make a new observation in the maximum point. You fit a new curve. Find the maximum of this function. That maximum is here. So you will try this experiment. When you try this experiment, you will see that the function value is actually not this, but this. You will get a new curve. You find the maximum of that new curve. Based on that maximum, you try a new experiment. Okay? So you tried this experiment, fit a new curve that has a new maximum here. You try this experiment, and you do this till you converge somewhere, and at some point it will converge to the maximum of your function.
So we pick the maximum of the curve despite the fact that it may have tons of uncertainty.
Exactly. Yeah. So this Thompson sampling is very naive, but that's what you do. Yep. Yep. And you can prove that under some conditions it guarantees to get to the max. Right, so under some conditions you can converge to the global. Because you, in each time, you check the global maximum of the function you fit, not just the local maximum.
Yeah, but then maybe the actual global maximum, your estimated function is very low at the actual global maximum, and you never try that experiment or something.
Right, so you can prove that under some conditions it have enough power to do enough exploration for you. Okay? Okay, but indeed this is very naive because it doesn't consider the confidences. So there's an improved version which is called upper confidence bound method for Bayesian optimization. And this is how it works. Again, you have a function that you want to maximize, looks like this. Instead of just fitting a Gaussian process, as we, a function with Gaussian process, as we said, yep? No, they could be anything. Yeah, we don't assume independence among the features. Okay?
And so there can be constraints on the intuition.
Yes. And indeed, if you have more knowledge about the features, you could do something better than this. All right, so as we said, with Gaussian process, it has the benefit that you can also not just predict a regression function, but uncertainty as well about that regression function. So we will use that. So, right, so say we are here. This is my point in the training data. And then with Gaussian process, I can fit a curve with some uncertainty. And this is the, this shaded area is my uncertainty. And I will find, when I optimize, instead of just optimizing the regression function, I will optimize the regression function plus its uncertainty, and that will be that point. So I will try this experiment here. I try this experiment as the function value. It reduced the uncertainty, but now I have big uncertainty here. So I will try this experiment. And I'm here, and now the Gaussian process regression provides this shaded area uncertainty. That's the point where the uncertainty is maximum, so I will try this experiment here. And you continue this till convergence. And you can prove that this Bayesian optimization, under some conditions, again, will find the maximum point. Okay, so the take-home message here that we have Bayesian optimization methods. We discussed two. One is the Thompson sampling, and the other is Bayesian optimization with uncertainty intervals. They can be used to optimize functions when function evaluations are expensive. And they don't use gradient information. Questions about this? Yep.
Comparisons of like how fast this algorithm gets compared to like some kind of gradient estimate if we had something like that.
Right. So one, if you have gradient, you might just converge only to local optimum points, but they can converge faster to local optimum points than they would do.
Is there like an order of magnitude estimate?
So it depends on conditions, though. And so, yeah, so they could, so it depends what kind of conditions you assume. Under some smoothness conditions, they are pretty good too. But still, gradient descent can be much, much faster than these things. Question?
So we have seen Thompson sampling for fitting neural networks, for example.
So,
So the difference between this and the other method, there again we have a Bayesian network and every parameter is a Gaussian.
mm-hmm.
And each time you sample,
Yep.
and then you instantiate a network,
Mm-hmm.
right?
Right.
And
So the difference with Bayesian optimization, the only is that you use the uncertainty from the Gaussian process as well.
the uncertainty
Yep.
to sample
To sample. Yep.
instead of sampling.
Right. To where to sample the next experiment. Yep. All right. So another algorithm I quickly want to mention that we also generalized these Bayesian optimization algorithms to the case when we have multiple fidelity levels. So here the true function you want to estimate is f. That's what you care about, but that's very expensive to evaluate. And we assume that there are cheaper approximations of f, say f1, f2, and f3, where f1 is the cheapest but lowest quality estimate. f2 is a bit more expensive, and it has better quality. f3 is even more expensive with better quality. And we generalized Bayesian optimization to the case where the algorithm shouldn't just choose where to run the experiment, but it also should choose which function to evaluate. So on which function to run the experiment. So for example, you can use that with neural network training, where at the beginning you might just want to, say you want to find the best hyperparameters for neural networks. And at the beginning, maybe you just want to try smaller training sizes. And when you roughly know what is a good architecture, then you can increase the training size and try more expensive experiments. All right, here is a cosmology experiment that we did with this multi-fidelity algorithm. So we wanted to estimate cosmological parameters, such as the Hubble constant, the dark matter fraction, and the so-called dark energy fraction. And we had two fidelity levels. One is that we had the training data from, the training data were some observations from supernova, and it turns out that supernova properties can be used to estimate these cosmological parameters. And depending on how many data points we choose, that was one fidelity level. Of course, the larger your training set, the higher your accuracy is. And the other thing is that when we wanted to estimate the parameters, it turned out that we had to perform a numerical integration as well. And when you do numerical integration, you have a grid size parameter. The finer the grid, the better the quality is, but the more time consuming the numerical integration is. So we had two fidelity levels here. One is how big is the training size, and the second level is when we did this numerical integration, how precisely we wanted to do that. And here are some results that we got. So our algorithm is called Bayesian optimization with continuous approximation, BOCA. And here is the standard Gaussian processes with this uncertainty interval. That was this green line. And the point here that you should remember that when you have multi-fidelity levels, then you can exploit sometimes that, and you can do something better than the standard algorithms. We also used this approach to try to find neural network architectures. And this is a neural network architecture. I just rotated this. So I guess this is the input, that's the output. And that's what we learned on Cypher 10 data. set. It doesn't look like standard neural network structures. It has some skip connections, as you can see, just like in residual neural networks. These are convolutional blocks. So what we did is that we allowed the algorithm to use convolutional blocks, skip connections, but where to skip the connections that it had to optimize.
And was the length fixed?
And the length was not fixed either.
So how could the network learn how to index, like the parameters?
So it tried. So that was a maximum length, though, but it was not fixed to be. Yeah. Yep. And here are some results on the.
And the parameters
Yep.
that were optimized for was where every layer should skip to?
Yes, and what kind of, and also whether you want to use convolutional blocks or you want to use batch normalization. So there were a couple of these options. Where to skip connections, whether from
And the idea is that the output function, which is, let's say, how well we're doing cipher, is kind of smooth over those parameters. So skipping to the 11th and skipping to the 12th should be nearby, so that.
Right. Yeah.
Okay, I see.
Yep. The other, it was optimizing whether you need to merge two of these blocks to one, or you want to split them. These were the things to optimize.
How many parameters were there in total, for example?
I don't remember. So there were tons of these things, but
Do these things that you relate fast ones, the number of parameters increases a lot, like 100 or?
so the parameters were. So it depends how we count the parameters. So we are talking about hyperparameters, not the parameters of.
That you're optimizing.
Right. So in each place, you were allowed to use either convolutional blocks or other kind of blocks, whether you wanted to use batch normalization or not, these kind of parameters. So the number of actions were not that big, but you have multiple of these actions that you can take in each.
So all of them, because yes, there are multiple. So let's say there are 100 in the order of 100 or 500, like.
Oh, it's
1,000.
bigger than that, right?
1,000.
Yeah, I think it's even bigger than that, right?
I see.
We should check on that, but much bigger. Because in each location, you can either decide, do I want to use batch normalization or not? Do I want to connect this to here or here? Right? So it's tons of parameters. And so here are some results on the accuracy. Our algorithm is called this Nesbot, and we found that this kind of architecture that looks quite ugly actually is better than, say, VGG19, that most often people use. So it seems that still there's some place to improvement on the structure of these neural networks for image classification. All right. So the take-home message from this is that we have algorithms for multi-fidelity optimization. I didn't discuss the details of that algorithm to save some time, and they can be used for cosmology or neural network architecture search, and we have code available if you want to try that out. These are still time-consuming because you need to train those neural networks, but at least the algorithm can decide how much training data to use for training.
So could we discuss a bit the relation between this Bayesian decision gaussian process versus reinforcement learning of those actions for architectures that other people have considered where they sample an action, let's say batch norm here. Then they get the reward and they have this reinforced style.
So let's do after class, because I want to show some
I see.
couple of other things first, and then we can come back to that. So another algorithm I want to mention is a myopic decision maker for design of experiments. And this is the setup. That the decision maker chooses an action that will be your experiment that you want to run, say in a chemical experiment, and then you observe an outcome of that chemical experiment. And you also assume that what you observe, this y of x, so of course it depends on the experiment you run, but it also depends on parameters that you don't know. Those are theta star, and you want to estimate those parameters. And you will, in t rounds, you will collect data. So xj is your experiment you run, and yxj is the observation of the experiment. And the goal is to minimize the penalty function that depends on the data set that you collected. And it can have, for example, this kind of form that from the chemical experiments I run, I want to estimate the solvation energy of my mixture. I want to estimate the viscosity of my mixture. And I want to find what was that experiment that had maximum conductivity. So you have multiple goals here put together. One is for each experiment, I want to estimate its properties, like the solvation energy or viscosity. And the other is that for all of these experiments I tried, I also want to know what is that experiment that maximized the conductivity. Okay, so based on these three goals, I can create a cost function. And the goal is to recommend experiments such a way that would minimize this cost function. Does it make sense? So if we want to recommend an experiment that minimizes this cost function, and the cost function has multiple goals in it. The other thing that's interesting here is that what we want to estimate, like solvation energy, that's a function. Because for each experiment, I want to predict the solvation energy. Similarly, the viscosity is a function for each experiment, like I mix different electrolytes. For each mixture, I want to predict what would be the viscosity of that mixture. And conductivity, that's a real value that I want to estimate, is just the maximum of all of these possible conductivity values. Okay, so in this goal, in this case, the goal is to estimate two functions and one real valued output, and I put everything into this cost function. Question? Yeah.
These are completely disjoint functions with completely disjoint parameters, and then we'll, it's a joint search problem that both learns to predict.
So they have the same argument x, and from that x, the experiment, they would predict the solvation energy and the viscosity of the same experiment. An experiment is mixing different electrolytes, and for any mixture, x, we want to predict its solvation energy or its viscosity.
I see. And they use the same kernels in the Gaussian process, or?
So we use the same, but maybe it's not optimal.
I see.
All right, and this is how we did this. Maybe to save some time, I just keep this algorithm. It was just a greedy algorithm that tried to estimate this expected value, which says that if I run this, imagine I run this experiment, I will try to predict what would be the result of that experiment that I would get. And we use that in the optimization process. But what I want to show is that here are some results. This is the cost function. These are the number of experiments. The smaller this cost function, the happier you are. And random is just a random search method in the parameter space. Grid search, that's a grid search in the parameter space. This black curve we can ignore for now. That's just the kind of theoretical optimum approximated in a weird way, but this is not a realizable curve. And the blue is that what we proposed. So what you can see here, that if you use this myopic experiment recommendation, you can do better that scientists often tend to do, that they just do a grid search or random search. Okay, so that's what you need to remember, that in many of these scientific problems, using these Bayesian optimization tricks, you can do better than 99% of the scientists do, that they just do a grid search kind of thing. Yep.
So given a training set,
Mm-hmm.
this Gaussian process just spits out, expected value, and so it's
Yeah.
just, that's it.
Yeah.
But the nearest neighbor kernels are very important. That's the whole point of representation learning, right?
Mm-hmm.
So what does it mean, two things to be similar versus dissimilar?
Right, so I agree. So the kernel, it depends a lot on the kernel.
Right, which is like the learning parameters of the Gaussian process, which we may need another Gaussian
Exactly,
process.
right. So you can do it in a hierarchy
So, I see,
too.
so
Yeah.
people do that and fit.
Yep.
I see.
But then, of course, you need even bigger budget.
Bigger,
Right.
right.
Yeah. The other thing that the other drawback of Gaussian process is that everything is Gaussian. Even the prediction is Gaussian. And maybe the real life is just not Gaussian, but still it would approximate everything with the Gaussian distribution. So there's a new direction now to replace Gaussian processes with neural networks, where the neural networks would output a real number just as they do, but they would also output uncertainty, how uncertain the neural network thinks they are about prediction. Okay, so the Gaussian process is just one way to do Bayesian optimization, but you can replace that Gaussian process with any kind of regression method that can output predicted output and an uncertainty.
So what you're saying is the basic thing is this limitation that the y needs to be connected to the axis in this very special
Yep.
way.
Right. Yep.
I see.
All right. So let me quickly go discuss other things. Right, and I also want to mention another kind of problem that was very important in many scientific problems, and namely, most of the time when we deal with regression or classification, we assume that we have input feature vectors. The observations are just some vectors. And there are many scientific problems where that's not the case, where the input is something more complicated. So for example, when I deal with, we have scientific problems with astrophysicists and cosmologists, some of the problem is to predict properties of the universe or predict properties of the galaxies. But when you look at the galaxy, what the galaxy is a set of stars. What the universe is a set of galaxies. And we need machine learning algorithms that can operate on this set of objects, where some galaxy might contain these many stars, and another galaxy might contain many more stars. So the set of the sizes might be different as well. And now we need machine learning algorithms on this. And the question is how to do this. Right? So I want to have a machine learning algorithm, either classification or regression, that can take input sets, say sets of vectors, and then what to do. So I'm curious about your opinions, what to do in this case. The problem is clear, right? So I want to create a regression algorithm where the input, instead of a feature vector, it would be a set of vectors. And sometimes the set would contain 100 elements, sometimes it would contain 2,300. Yep?
So we have seen here in the previous lecture about predictive models, and they need to consider the objects in the scene, and some scenes have more objects than others.
Right.
So we have talked about graph nets that aggregate the inputs and
Okay.
etc. But I don't think we've seen as a forward model for physics, let's say.
Right, so here is one thing that we can assume that when we have a set of objects as input, you might assume that the set of objects was sampled from a distribution P. We don't know that distribution P, we just have observations set of objects. Okay? And generally, how regression algorithms work. You have two inputs. Somehow we need to compare these inputs. Either calculate the Euclidean distance and saying if the Euclidean distance is close, the predicted outputs should be close to each other. Or when we do with support vector machines, we calculate the inner product between the inputs and do prediction based on that. So when we have sets as observations, we need to introduce either an inner product between these sets or a Euclidean some kind of distance between these sets. And again, the assumption is that each set, this set here, is sampled from a distribution. This set is sampled from another distribution. We don't know those distributions, but if, say, the distribution of this set is P, the distribution of this set is Q, at least I can define distances between P and Q easily, and then I can use my sets to estimate that distance. So, for example, this could be a Euclidean distance between two distributions where the densities are P and Q. This could be the Kullback-Leibler divergence between P and Q. And this is the so-called Rényi divergence between P and Q. So P and Q are densities. I don't know them, but I have some samples from P and I have some samples from Q. And the question is, first question, how can I use those samples to estimate these guys? Does it make sense? So you have some samples from P, you have some samples from Q, you want to estimate these quantities either that you can see here. Okay, so for example, formally the Rényi alpha divergence estimation problem is that we have n sample points from P, m sample points from Q, and I want to estimate this guy here. Yep.
Is it important that this like distance metric is well behaved? Like, what if we just made some kind of adversarial network that just wanted to the same distribution as zero?
Right, exactly. So they have to behave well in some sense. Otherwise, we cannot do really machine learning. So for example, with that distance you just mentioned, it's impossible to any reasonable algorithm. But the Euclidean distance, that's more reasonable.
What if it's like the adversarial network gives you a probability of the continuous?
So I don't know. So let's discuss that after class. But let's start with something simple. So I already told you that this is the distance I care about, like the Euclidean distance, or these Rényi alpha distances. The question is still how to estimate those. Okay, so I don't know P, I don't know Q, but I have samples from P, I have samples from Q. And the question, how to estimate this? And I'm looking for ideas. Does it make sense, the question? You have some samples from P, some samples from Q, and estimate this thing. So, okay, so here is an obvious approach. I have samples from P. I could estimate the density of P with those samples. I have samples from Q. I could estimate the density of those samples from Q, and I could plug in the estimated densities here. And here, calculate this integral somehow. That's an estimate. The difficulty is that density estimation in high-dimensional spaces that we typically deal with suffers from the curse of dimensionality. And you might get a very bad estimator that way. So you might ask the question, is there a way to estimate this quantity without ever estimating P and Q? Does it make sense? I don't want to estimate P, I don't want to estimate Q. I want to estimate their integral. Or similar in the Euclidean distance. I don't want to estimate P, I don't want to estimate Q. I want to estimate P minus Q integral squared. Yep?
I don't have a fully formed idea, but what if you kind of like pretend you have some kind of important sampling level? Just like multiply by P inside the integral. And then
We don't know P. We don't know Q. Right? So you just have samples. You don't know P, you don't know Q. Yep?
So how about add some samples from Q into P and see what is entropy or information gained from that?
But you need to estimate the entropy. And how you would estimate the entropy? So the entropy would be, I don't know, integral P log P. But again, you don't know P. Does it make sense? So in statistics, this is called integral functional estimation. And it turns out that you can estimate all of these quantities without estimating P and Q. And I think that's interesting, right? That you don't need to estimate P, you don't need to estimate Q. Still, you can estimate these guys. And quickly, I just want to, I will tell you how to estimate this quickly, but first the motivation for this algorithm. For example, I want to classify soccer players. Good soccer player, bad soccer player. And here are 3 soccer players, and I collected where they try to score goals. Okay, so Owen, he tried to score, this is an old data, so Cristiano was in the Manchester United. So Owen tried to score goals when he's far from the goal, as you can see. Rio only tries to score goals when he's close to the goal. Cristiano, whenever he gets the ball, he tries to shoot, right? So that's the data set. Each soccer player has their own data set. And I provide some labels because I want to know who is the good player, who is the bad player. Or some experts provided some layers, and they say they labeled good player, bad player. And then the question is, when you got a new set where a player tried to score goals, you have to predict whether that's a good player or bad player. Okay, so this problem is called distribution classification. And let me just quickly come to this slide. So as we discussed, for many of these regression problems, when you have inputs, you need to know the distance between the inputs. In our case, the true inputs would be densities, but we don't know those densities. We just have samples from those densities. And we want to estimate the distance between those two densities, for example, with this term, integral p to the alpha q to the 1 minus alpha. And just want to quickly mention one estimator because I think it's interesting. So here you have some sample points from P, some other sample points from Q, and I want to estimate this quantity, integral P to the alpha Q to the 1 minus alpha. This is what we do. We will use k nearest neighbor distance estimators. Say you choose k to be 2, and for each point among the blue points, you calculate their second nearest neighbors. So for this guy, I think this would be the first, this would be second nearest neighbor. And you denote this distance with rho 2i. Okay? So for each point in your training set, among the blue points, you calculate its second nearest neighbor among the blue points. And you also calculate its second nearest neighbor among the red points. So this would be its first nearest neighbor, this is its second nearest neighbor. Okay? You do that for all blue points. And then you can calculate this rho 2 and nu 2 quantities. Okay? And our goal is, again, to estimate this integral p to the alpha q to the 1 minus alpha quantity. And interestingly, you can prove that this guy, that's here, so we have n points from P, n points from Q. This is the dimension. In this case, is 2. We want to estimate integral p to the alpha q to the 1 minus alpha. Gamma is just a gamma function. You can prove that this guy converges to this term if you increase the sample size. Okay, you don't need to see why it's true. That's quite complicated. But what you should see, we didn't estimate the densities. And still it converges to that distance that we cared about. And when we have a distance, we can use that in machine learning problems. You can either do k nearest neighbor regression, if you want. Can you tell me a kernel, your favorite kernel in support vector machines? Gaussian. So how is the Gaussian? Looks like exponential minus x minus z squared norm. We can replace that x minus z squared norm to this distance. We just measure how far x is from z. And you might get a new kernel that you can use. And then you can use support vector machines now on sets. Question?
Can I estimate that p divided by q is that?
Yes, there are methods for p over q as well. Yep. So that's called likelihood ratio estimation. Okay. There are methods for entropy estimation as well, but I don't show it to you now. But I want to show that after we introduce this distance between distributions and we created support vector machines on distributions, now we can use that for scientific problems. One scientific problem was that scientists cared about to estimate the mass of galaxy clusters. It's very important for them because galaxy clusters are the largest gravitationally bound objects. And if we know their mass, we can calculate the light in them, and we will know from that how much dark matter is there. So somehow we want to know the mass of galaxy clusters. But we cannot just walk to the galaxy clusters and measure them, right? So we want to predict their mass from observations. And what they did is that they generated simulated data that they trusted. So they simulated galaxy clusters with known masses. This way, we had input-output pairs, simulated galaxy clusters with their mass. Each simulated galaxy cluster could be considered as a set of galaxies, and we can use this distribution regression problem on them. Okay? And here are some results. This is the relative error, the predicted mass minus the true mass divided by the true mass. That's the predicted error. And what we want is that we want this predictive, we want these curves to be as peaky as possible. So we want the relative error to be around 0 and with as small variance as possible. And here you can see 4 methods. These 2 are the standard methods that physicists used in the past. And these are 2 support vector machine-based methods when we generalize support vector machines to distributions. And you can see that these are more peaky than what physicists used. And it's interesting that these methods don't know anything about physics, right? Still can do better predictions than physicists put together their knowledge in physics. So one lesson is that even if you don't know physics, if you have large enough data set, you might be able to do better than what we can do with all our physics knowledge at this point. Does it make sense? So we generalized support vector machines to be able to do regression on sets. And then we can use them for these scientific problems. Another thing we did that, okay, we generalize support vector machines to sets, but your favorite models or predictors are neural networks. So now the next question is, can we generalize neural networks to sets as well? What it means is that the neural network would get input as sets in some form. And I want that neural network to be invariant of permutation of the sets. So for example, the set could be a list of vectors. But if I permute the element of this list of vectors, because it's just a set, the neural network should predict the same thing. And we created neural networks with that property. And what we did, that we used these neural networks to predict the parameters of our universe. And what we did, again, that no one knows the true parameters of the universe, but scientists can create simulated universes with known parameters. And here you can see some simulated universes. Each dot is a galaxy. Okay? This is one universe with some parameters, another universe with some parameters, another universe with some parameters. And then we use these neural networks that was able to operate on sets and predict an output for regression. So the input is going into this neural network, and it tries to predict the parameters of the universe. And here you can see the results. So this is the ground truth. That's the prediction. Ideally, you want to be on this black line. So you want the prediction, ground truth to be the same. So you want the prediction to be the same as the ground truth. And the blue crosses, those are the predictions that the neural network makes. And the red dots are the standard methods that scientists used before. And again, you can see that these neural networks do better prediction on predicting the parameters of the universe than the standard methods, although they don't know anything about physics. Right? We just had a large enough data set, and somehow they extracted information that's important to predict properties. Yep?
Was this neural network designed using the same basic processing you explained earlier?
Actually, no. So we just, so we could have done it, but we didn't do. So we didn't do hyperparameter optimization on this. What important part for us was only to generalize neural networks to be able to operate on these sets. But you are right that after that, you could even optimize the hyperparameters for these neural networks, but we didn't. All right. Finally, I want to mention, how many minutes I have left? 2, right?
Minimum 2, maximum 12.
Okay. You have a question?
Yes. So these previous slides data, we have a lot of those data. We have
Yes.
data too.
Yes, because, yes.
So the difficulty is when both we don't have good features and we don't have a lot of data.
Exactly. Yep.
That's the problem.
Right.
I see.
Yep.
So for the previous, like the previous slide, the input, how do you unify the input? Because it could be either number of vectors in a set.
Right, so what we did, that it was just a list of these coordinates where there's a galaxy there, and it was a long list. And we wanted to make sure that the neural network is invariant. If you reshuffle the list, then it should still provide the same prediction. Another way to do it is that from these, you can also create a histogram and then create a neural network that can work on histogram. So in that case, we need to deal with 3D convolutional neural networks instead of 2D that we typically use in images. I also want to mention another science problem. It's called the weak lensing challenge. So scientists take millions of pictures of the sky, and some of the pictures will look like this, where this is a galaxy, there's another galaxy behind this galaxy, and that distorts light. Because of that, we see this galaxy like this. And scientists like those kind of images because they can tell information about the mass that's around there. Because the bigger the mass, the easier you can see these lensing effects. So that's called gravitational lensing. And now the challenge is that among the millions of images that are taken by telescopes, how to identify those images that show gravitational lensing. Okay? And this challenge was so important that they actually made an official challenge where, I don't know, many different teams tried to compete with this for a year to get the best algorithm that can classify images, whether there's gravitational lensing there or not. And 2 weeks before the deadline, we realized that there is this challenge, so we decided to try it.
So it's just image classification.
It's just image classification, yep. And so the interesting thing was, so we only had like 2 weeks, but my students and some cosmology students, they decided to try it. And we won the challenge. And some of the cosmologists got a bit mad that they were working weeks on this. But at the end, it was just an image classification problem. So a modified ResNet that we modified a bit with hyperparameter tuning using Bayesian networks worked better than the standard ResNet that our competitors tried out.
The standard ResNet.
Yeah.
Oh, so it's all the hyperparameter thing that makes it.
So it made some, yeah, right. And so since then they are using this, and this will be a method in some of the telescopes.
But the other competing teams cannot have worked on this for many weeks. They just downloaded the ResNet.
So that's what the competitors did, right? That either they didn't even know about ResNet, or those that they knew about ResNet, they just tried the standard ResNet.
That's so funny.
Yep.
It's competition.
It was a year ago.
I see.
Yeah.
And did you use also pre-trained features, or do you start from scratch?
We started from scratch, so we just had these images.
I see. Oh, it's directly.
Yeah, yeah. All right, and finally, one more problem I want to quickly mention is scientists like to simulate the universe, and they want to put simulated galaxies there. And we can use adversarial neural networks kind of methods to generate more galaxies. So you have some galaxy images, and you can train GANs or other generative models to generate more galaxy images. And now they work pretty well. So these are real galaxies from a galaxy survey. And these are artificially generated galaxies. And it's So even experts cannot tell the difference at this point now, and we can use these methods to simulate galaxy images much faster than they did in the past, plus with better quality.
Conditional generation, like I give you some parameters.
And we can do conditional generation as well. Yep. So for example, you might say, hey, I just want to simulate elliptical galaxies. Yep.
Also that like the Mach ones are just generating one of 10 different types of galaxies.
Right. So that's a good point. So and generally that's an issue with GANs, right? But we try to look at with experts, and it didn't look like a serious issue in this case, but that's a valid question. To make sure that when you generate, you don't just repeat your training set, for example, right?
Because like in the picture, it looks like the Mach ones are very.
Right. So there are some ways to check on these things, and it didn't look like a serious issue in this case. Right, so for example, sometimes what people do is that they do interpolation in the hidden space and generate for each and see whether that changes smoothly or not. So there are some tricks, but you are right that people have to be careful.
It's not even GAN, this is pixel CNN.
Yeah, it's even pixel CNN, yeah.
But can I ask you something? This Bayesian optimization, I mean, how many experiments did you have to run to win the challenge here?
So it was not too bad. So again, we only had like 2 weeks. So we just tried a few. We didn't even need to change much the ResNet to get better results.
But let's say 10, 20, 30.
I would say around 100-ish.
Around 100.
Yeah. Yep, so I should stop here. Just want to mention one more thing that I didn't talk about, that we also have a big data problem here. This is a telescope called LSST. It will collect 15 terabytes of images per night. And then we will have each night 15 terabytes of new images, and then what to do with that, right? So no one will look at them. So we need machine learning algorithms that can quickly classify them, find the more interesting events, see if there's something scientifically surprising. So that's what we are working on now. So thanks for your attention. If you have questions, then please contact me, and I'm happy to discuss them with you. Thank you.